This is our lecture 3 today. So, if you can recall what we learned uh, last week, we learned about some of the mechanical properties of materials, right? So, today also we will continue the same topic on the mechanical properties of materials, right? So, last week I explained you about like these things, right? The information that you can get from a tensile test, right? How you plot the data, then from that graph, we call that engineering stress strain curve. From that graph, how you obtain the some important information about the material, right? For example, the material's tensile strength, yield strength, right? The Young's modulus, those information we can obtain by conducting a tensile test, right? So today I will start with that one, right? So the example I took, that stress strain curve last week, is but basically is for a metal, right? So usually for a metal, it will have this kind of a stress strain curve. Not all the metal, but in general, we can say like that, right? But we are talking about that stress strain relationship of materials. So if we consider different material, for example, other than metal, ceramics, glass, then elastomers, plastics, so those things, they have different shapes for their stress strain curve, right? For I listed some common materials you find when you use them to make products, right? For example, if it is a ceramic or glass or concrete, the typical diagram of a strain behavior will be mostly look like this, right? So does this mean? So we can see from the graph there is a linear elastic region of stress strain variation. After that, there's no any plastic region like in metals, right? This graph is characteristic for ceramic, glass, or concretes, right? Which means they don't show plastic behaviors. What is plastic behavior or plastic deformation? Which means before, if you apply certain force on that material, right, at a certain load level, that means at a certain stress level, that material will break. But before break, it will have elastic region. For example, that means once you release the applied load, it will become its original shape. And then can be another region when you apply the load, and when you remove that load, that it will not become its original shape. So we call it has undergo a plastic deformation, right? So ceramic, glass, concrete, these usually don't have that plastic behavior. That's why their stress strain relationship is like this, right? Then if you talk about elastomers, like elastic materials, right? Then they have, I explained you about materials which have non-linear stress strain relationship, which means when you apply certain force, it will stretch. After you remove the load, it will again become to its original length. But that deformation is not linear, right? It will undergo long strains at certain stress levels, right? So this kind of behavior we expect from elastomers, right? So, for example, for thermoplastic material, above Tg means above the glass transition temperature, we can, it's a kind of plastic, we can uh, uh, make this material into different shapes or thin sheets like that, right? So that material will have this kind of stress strain uh, relationship. If you see here at this strain level, stress level, it undergo very large strain, right? So this kind of behavior we can expect for a thermoplastic material, right? You see that depending on the material, this stress strain relationship vary, right? So here again I listed some to explain you their variation. That means the variation of their yield strength in different material groups. For example, ceramics, metals, polymers, and composites. So this is the yield strength variation, right? This is the yield strength. So these materials, the ceramics, usually they are in the upper scale. That means they have higher yield strength even though they don't show plastic deformations, right? So metals, they have also high yield strength. If you check this scale, right, it increase in this direction, right? So polymers, they don't have much high yield strength compared to ceramics, metals, and composites. Okay. So if I give you this type of chart, right, this is a stress strain graph of different material. So based on their basic shape, can you identify what can be the material A, what can be the material B, what is C, what is D, like that? So you should be able to uh, just you would try to identify the material based on their shape, right? Yeah, A, it can be a metal. C, again, it can be a metal because you see this slope, right? This slope and this slope, the slope is different. That means we have an idea about their Young's modulus, right? See, someone said, right? Who's that? Nimesha? Yeah, Nimesha. Oh, Nimesha. I am not sure, right? So Nimesha, okay. So he said that A is metal, right? B is glass, ceramic, like that, right? D can be a linear, non-linear elastic material. We exactly cannot say what is D, right? So like that, it's enough for you to identify that material. You have to have a guess about their the nature of the material depending on their stress strain curve, right? So as this is a first year course, we don't expect you to learn much more complex things, right? This type of basic things, it's enough for you to learn, right? When you move further in your semesters, you will learn depending on their, depending on what you choose as your specialized field, you will learn required more details, right? Right. So I told you I will give you one example on how to use the data that we obtain from a tensile test to plot the engineering strain curve, right? So I remember this one. When you plot the engineering stress strain curve, you always consider the initial specimen diameter and the initial specimen length to calculate this strain and stress, right? So here I have listed the data that you can obtain from a tensile test, right? So doesn't usually we use that Newton and meter as the units, but it's okay. I here put that lb and inches, right? The stress in psi, that means pounds per square inch. So doesn't matter, right? So these are the load levels that you apply in a tensile test, right? These are the change in length of the specimen, which means once you apply 1000 lb, there is a change in length in the specimen 0.001. Once you apply 3000, change in length is 0.003. Right? So you have to, in order to plot that engineering strain curve, you have to calculate the stress and strain. Right? Can you try at least one or two from this based on this data and tell me the values? Right? If you know to calculate one, if you have Excel, you can calculate all, right? So maybe you can calculate for this one. For 1000 load, change in length is this amount. So can you calculate stress and strain based on the diameter of the specimen is 0.505 inch, initial length 2 inch. Maybe I will give you 5 minutes. Can you try and tell me the value? Did anyone calculate? So did you get the values like this? It just you have to divide the load by the this A naught, initial or sectional area, right? So this is the diameter. Area means 5d squared over 4, right? For a circular bar, right? In that case, I hope you can calculate this stress and strain values. Okay. Then what you can do is you calculate the stress strain and you plot it in the graph, right? So this axis is the strain, this axis is the stress, right? Once you plot it, you will get the curve like this. No need to convert it to SI units, right? Because this is just example. No, usually when I give you assignment or any other type of assessment, I will definitely give it in SI units, right? So for this example, you don't have to calculate it like that, right? So then you can get the modulus of elasticity from the from this slope of the linear region, right? So slope means you divide this delta S over delta E. That means you get 2 points in this linear part, right? You get the corresponding stress level and you get the change, that is the delta S. Delta E means the strain difference corresponding to these 2 points, right? That means Young's modulus of elasticity we calculate, I hope you remember, from the linear region of the stress strain curve, right? So slope means what? This angle theta, right? Tan theta. So tan value means this height over this length, right? So you can select 2 points in the linear region and you can calculate the modulus of elasticity, right? So from the maximum point, because this is not exactly the shape, because I changed the axis to exaggerate this part, the linear part, so you can identify how to calculate the modulus of elasticity, right? So maximum point of the curve we call this corresponding stress in here we call tensile strength, right? So once you plot the 2% strain line, you can get the offset yield strength. You remember how we plot that, how we obtain that offset yield strength, right? We draw a parallel line to this linear part through the strain of 0.002. 2% mean 0.2% mean it is 0.002 strain, right? So you plot a parallel line to this linear part, and when it touches the graph, the corresponding stress level we call the offset yield strength or the yield strength. Right? So this is how we plot the data and obtain some information. Right? So I will give you example, and I can now then I see whether you understand that concept, right? So you first do this example, and I will ask someone to give the answer, right? You don't have to send me. I will ask from someone, 1 or 4 people maybe, right? There are 4 parts, right? What's the answer? Because I need to know whether you understood how to get certain information from the stress strain curve, right? So you don't have to afraid, because we are learning. This is example only. This is not a assessment. That means a formal assignment, right? So please do this example, right? So is this graph clear for you? I hope it is clear enough, right? I will explain a bit about the graph. So this is the stress strain curve, right? So this is the linear part. Since we cannot obtain the values because the linear part is, it has very steep slope. So what they have done is they have expanded this part, the scale, right? So this inner part is the expanded this linear part, right? You see here, this is 0, this is strain 0.005. That means some small part in here, they have enlarged, right? Some small part in that initial region, they have enlarged, right? So it is this part, right? So you can use this part and the whole graph wherever necessary to calculate, to solve or to answer these 4 questions, right? Maybe I will give you 10 or 15 minutes, right? We can see the answers later. Okay, shall we discuss the answers? Right. If we read the question, from the tensile stress strain behavior for the brass specimen shown in figure, determine the following. Right. The first question is the modulus of elasticity. Right. That means you can get it from the slope of the linear part in the stress strain diagram. Right. So the linear part is enlarged here. Right. So for your easiness, I just mark 1 point in the linear part. That is corresponding to, this is that offset line, right? So this point is 0.002, right? So corresponding stress value I mark for you, it is then around 165, right? So let me ask the modulus of elasticity value from someone. Maybe from A letter. Anuradha, I unmute your microphone for you. Right? So what did you calculate the modulus of elasticity? Or if you calculate, you can send me the value if you cannot talk. If not, can someone tell me? Can someone tell me the value you got for the modulus of elasticity?
82.5.
What is it?
82.5 gigapascal.
82.5. Okay. So you got it correct. What's your name?
Araka.
Huh? Okay, you are correct. Then the correct value is 82.5 because I will put the answers one by one because there may be students that they are still cannot calculate it. Okay, so first one, the modulus of elasticity, right? So that is you have to calculate E, right? So E is equal to delta sigma over delta epsilon, right? Delta sigma over delta like this, right? So you can substitute the values, right? Delta sigma means corresponding to 2 points, you put the stress values, right? If we write it, we can write it like this, right? So then we have to, according to this one, this is when you select 2 points in the linear region of the graph, right? So I select 1 point here and 1 point the origin, right? So corresponding to this point, first you need to know the stress and strain. That means sigma 2 and epsilon 2, right? Then corresponding to other point, you also need to find the stress and strain. So my other point is the origin, so it is 0 and 0, right? So you can put the values, right? So corresponding to this point, the stress value is, I already gave you the value 165. Then corresponding to other point, it is 0, right? So strain 0.002 minus 0, because corresponding to this point, this is the strain, right? So I choose the point where that they have drawn the offset yield strength. So it is 0.002, right? So once you calculate this answer, you will get 5 megapascal, right? So this is how you can attempt to the first part of the question, right? So I hope this is clear for you, right? Someone can choose another point, right, somewhere here in the linear part, but it makes your calculation difficult, right? Because you have to find the coordinates corresponding to that point again, right? This way is easy. So the second question, the yield strength at a strain offset of 0.002. That means this is the strain offset. Okay, someone asked to explain again, right? So Young's modulus means it is the slope of the linear part of the graph, right? So this is the graph, right? So this is the linear part, right? This is the same graph, but they have expanded this initial part of the scale. So you can clearly see the slope, right? So this is the linear part. Slope means you have to get the angle that is tan theta value, right? Then if you say this is theta, that means the slope, right? Then it is this height divided by this length, right? So how you calculate this height? If you know this value, you can calculate this height, right? So corresponding to this point, you can calculate the stress from the scale, right? Here's point is 0. So that's why we put 165 minus 0. Because to calculate the slope, you have to choose the 2 points in a okay. You have so many questions, right? Let me explain this first. Right. So you have to choose 2 points. For the easiness of the calculation, you can select 1 point in the linear part as the origin. Another one, you can select any point, right? Another possible ways you can, for example, this line is corresponding to the stress of 150, right? Then you can draw a line to this linear part, and you can find the corresponding strain for this 150 value from this scale, right? Any method is correct, right? Remember, it is always the stress divided by the strain. You have to for the slope you have to choose 2 points, right? Then you can divide it like this to find the elastic modulus, right? So megapascal means units what? Actually, this is not megapascal, right? This is gigapascal. This is gigapascal. Okay. Yeah, it is gigapascal. Okay. Now I think this is up to this point is clear. Right. So part B. For the part B, the yield strength, offset yield strength, right? That means you put a parallel line for this linear part across the point 0.002 strain, right? Yeah, many of you identified it correctly because it's already given, it is 250, right? So the second answer is yield strength is 250 megapascal. Okay. So the third question, the maximum load that can be sustained by a cylindrical specimen having an original diameter of 12.8 millimeter. It asks to find the maximum load that a cylindrical specimen can have if its original diameter is 12.8. That means without change in this original diameter, what is the maximum load it can take? So let me see. Yeah. Yeah, I see that one person gave me the right answer, and someone again asked about the part B. Part B. In here, it is already given the yield strength 250, right? If it is not given, how you have to plot? You have to draw a construction line. The way is, this is the strain axis. You have to select the point 002 strain. That means in this scale, you have to find the point, the value with 0.002. Then across that point, you have to draw a parallel line to this linear part across that point. Right? Say that point is somewhere here, right? Then let's say this is the 0.002 strain point. So you have to draw a parallel line to the linear part, right? So here I'm not sure this is exactly the same correct point, right? So once you draw the parallel line, when it touches the curve, right, the corresponding stress level we call offset yield stress. That's how you calculate it, right? In this one, the value is given yield strength 250. They have already done that construction, right? So the third question, I see that now there are more answers, right? Anyway, I will explain. The one who sent me the answer, Bilshi Piris, I think it's the correct one, 57.9, right? So the maximum load should be corresponding to the maximum stress that the specimen can bear, right? There is a maximum stress that a material can bear. After that, you remember, after that maximum stress level, that start necking and subsequently it will break. right? So the maximum stress means the maximum stress of the specimen that it can take, right? So that strength is the one we call tensile strength of the material, right? Tensile strength is the highest point of the curve and it is already given. It is 450 megapascal. This is the maximum stress level, right? So this, if the specimen diameter is this amount, how you find the maximum load? At this point, maximum stress means what? Stress means the maximum load over the original cross section. If you know the maximum stress and the original cross section, then you can find the maximum force, maximum load that can be sustained by the specimen. Right? So I will do the calculation. Maximum load, that is corresponding to maximum stress. That means corresponding to tensile strength. Right? So we can write maximum stress means maximum force over original cross section. Original cross sectional area. Right? So maximum force is equal to right, maximum force I will write as F maximum, right, maximum stress into the original cross section, right? So is equal to, here the sigma maximum means the maximum strength that the material can take, that is the tensile strength, right? So it is 450, right? So you can convert into Pascal. Pascal, and you have to multiply by the area, right? Convert megapascal to Pascal, you have to put 10 to the power 6, right? Then this for the cross section area, right? That is 9, right? Cross sectional area, you have to put that 5 into D is diameter 12.8 millimeter, right? So you can put 0.0128 to the power 2 divided by 4, right? So maximum force, maximum stress, that means the tensile strength into the original cross section area. Tensile strength is 450 megapascal. This is the cross section 5d squared over 4. This is 8, right? So you will get the answer 57.9 kilonewton. Right? You will get the maximum load as 57.9 kilonewton. Right? So the fourth question. Yeah. For the fourth question, I already received one answer, two answer, right? But I don't think those are correct. Any more answers? Actually, I will tell. The part D, the change in length of a specimen originally 250 millimeter long that is subjected to a tensile stress of 345 megapascal. Right? Actually, the answer can be little different if you didn't choose the corresponding point for the tensile stress of 345 as this point A. Actually, this I forgot to tell you, this point A is corresponding to the tensile stress of 345 megapascal. Right? Here it will be 345. Right? So for your easiness, I marked the corresponding strain as 0.06. Right? 0.06. So you know, if the applied stress, right? Applied stress is you see this 345 is larger than the yield strength of the material, right? Because it asks to find the change in length of the specimen when it is subjected to a tensile stress of 345 megapascal. You see that 345 value is larger than the yield strength. That means at this point, the material has already undergone plastic deformation. Right? So the only way you can get the change in length corresponding to this point is, that means in the plastic region, is by the graph. If it is, let's say, in this region, if it is, say, let's say, if they ask to find the change in length at a stress level of 165, so it is below the yield strength. So you can simply use, in any case, the calculated modulus elasticity without the graph, if they don't provide you the graph. But here you need a graph to find the change in length because the point A is in the plastic region. Right? So this is the strain value corresponding to the stress of 345. Now can you tell me the change in length? If you didn't take this point A as this 345 stress level point, it is simply What is strain? It is change in length over original length, right? So I will write the again the answer, right? Maybe in here, right? For part D, delta L over L naught, this is the strain, right? So delta L is equal to strain times the original length. Strain times the original length. So corresponding to 345, right? This strain is 0.06. 6 into original length is 250. That means 0.25 millimeter. Maybe you can put in 250, right? So you will get the answer as 15 millimeter. Yeah, 15 millimeter. Yes. Okay. Right. So this is the answer for the part D. So this is the if I ask the question from the mechanical properties of the material for your exam, right? So this is the maximum I can ask. There are no more information that you can get, right? Probably I will give you the, because you know that this semester is based on the online courses. So my major part of your exam marks, that means out of 100, will be covered by the assignments, right? Most probably around 40% of your marks will be covered by the end semester exam, right? So I have to give you more assignments, not very difficult ones, in order to provide that 60% of your final marks, right? So please, when I upload the assignments, I upload it into the LMS, right? So I give you that deadline, that means the date you have to submit, right? Please be careful to submit within the given period. Usually I will give you at least 1 week, right? At least 1 week, not earlier than that, right? So in that case, uh, please submit, because not like you submit the hard copy assignments. When you submit online, I can clearly see how early or how late you submit your assignment, right? So I can detect the late submissions. Since I give you enough time for the submission, I won't accept the late submissions, right? I will try to give you at least 2 weeks or 10 days, right? So therefore, please submit it on date. If you are late, I have to deduct some marks for that late submission, right? So next week, probably not next week, before next week, I will upload assignment 1 to the LMS, right? And if you have any question, you have to ask not the day of the last submission, right? You have to ask any questions early. You cannot say I didn't have internet connection today, I have to submit it today, then I need a extension, like that, right? That kind of things cannot happen, no, because some people, they say that if the deadline is today 12 p.m., they call me at 11:55 and say I don't have laptop, I don't have internet. So if you have any such question, you can send me an email. I can definitely give you excuses for those who don't have internet facilities or laptops to uh, uh, complete the assignment. But that one you have to inform me early. That's the only thing, right? So then I can,
Excuse me, madam.
yeah, yes.
Madam, මගේ LMS එකේ madam මේ material part එක පෙන්වන්නේ නැහැ madam.
පෙන්වන්නේ කියන්නේ මොකද්ද?
ඒ කියන්නේ ETC 1142 properties material කියලා මේ section එක පෙන්වුවාට එතනින් හර මේ cost එක එහෙම පෙන්වන්නේ නැහැ madam. කලින් upload කරපුවා මොකක්ද පෙන්වන්නේ
එහෙමද?
නෑ madam.
කවුරුත් මට කියෙන්නේ නැහැනේ ඒක මේ පෙන්වන්නේ නැහැ කියලා.
නෑ madam, මගේ එක විතර අනික් අයගේ පෙන්වනවා.
ඔයාගේ විතරයිද?
ඔව් madam.
මම මෙහෙම කරන්නද? ඔයාව මම unenroll කරලා ආය පාරක් මම ඇඩ් කරන්නම්. හොඳද?
හරි madam.
ඔයාගේ මට ඕනේනේ ඔයාගේ අර LMS එකට පාවිච්චි කරන email address එක.
ඔව් madam.
මගේ email එකට එවන්න. මම බලන්න ඔයාව අයිලා කරාම එක හරියනවද කියලා issue එක.
හරි madam, හරි.
එහෙම නැත්නම් ඔයා IT එකට පොඩ්ඩක් කතා කරලා ඒක විස්තර කරන්න. අනිත් අයට පේනවනේ නේද?
Hello, madam. Excuse me.
Yes.
Madam, there is a two section of properties of materials.
Two sections, please.
Properties is materials. First one is blank, and second one have our LMS materials.
Because that one may be the previous year one.
Yes, madam.
Yeah, you whatever, because you cannot enroll to that one. I think you cannot access.
Yes, madam.
Because all that students in this group, I enroll only to one course.
The second one has the all materials, madam.
Yeah.
I think so.
So you can prefer that one because I will upload the documents always into the same that module. The one I usually upload, right? You don't have to check other one, right? That is the old one. I already removed the participants and I think that's why it's empty. Okay. Yeah, I told you usually it will have to cover at least 60% from your final exam marks. Right, at least 60%. So in that case, from my part, maybe 3 assignments, because I told you that there will be another lecturer who do that polymer and composites part materials, right? So in my part, I will probably give you maximum of 3 assignments, right? So I'm not sure the Dr. Ajita how he will decide his assignment component, right? But anyway, it has to be at least 60 to 70%, right? So please use that LMS only to submit the assignment, and please don't send me the your assignment by email, right? Because you know I am doing another course. There are 160 participants now here. 160 participants. If I receive all the participants into my email, I cannot sort those into separate folders, right? It's very difficult, and there are higher chance to misplace your assignment, right? That's why I ask, please submit it only through the LMS, right? Don't send me to my email, right? Okay. Now I think actually I have an issue with the first part of the last week lecture, right? The thing is, I told you that I had that power interruption. So in that case, I have the raw file, the Zoom file, but still I cannot play it without converting to that media file. That issue is there. I am still looking for how to convert it, right? So I will complete. I will try to upload, because you know again otherwise I have to record 1 hour lecture from the first part, right? So I will try to that convert the file and upload. Okay. So the today's PDF I will upload by today, and the recording also. Right, recording maybe I will upload in the evening, because I think this recording will have more than 100 megabyte with the duration. Right, so I will upload the recording in the evening. Okay, so shall we move to the course? Okay, right, so I hope this type of question you can now understand and you can clear about, right? So we will move to the next part, right? So ductility is also a mechanical property of a material, right? So the definition is, the ductility means the ability of a material to be permanently deformed without breaking when a force is applied, right? So I told you earlier about that metals has uh, uh, plastic deformation region, right? But the ceramics, glass, they don't have that region. That means metals, they have ductile properties, but glasses, they don't have. We know that in practice, right? We cannot අදින්න බැහැනේ glass එකක් නේ. නමුත් metal, but when we apply a force, we can stretch it permanently. That means this permanent deformation, permanently deform, right? So we define this ductility as the ability of a material to be permanently deformed without breaking when a force is applied, right? So how to measure? We can use still the information from the stress strain curve also, right? So we have two ways to measure the ductility of a material. One way is the we call percentage elongation. That means permanent plastic deformation at failure, right? So we calculate it like this with this equation, right? So LF means what? LF is the distance between gauge marks after the specimens break, right? Because always we have a gauge length to measure the change in length, right? After we conduct, I don't have image, right? For example, we can draw a figure maybe, right? Before failure, after failure, maybe your specimen. Okay, we'll try to draw. Right, it can be like this, right? The other part also, I cannot draw it properly here, so don't mind that shape, right? Right, roughly this is the breaking point. It will be look like this, right? So maybe you measure the length of that specimen, let's say between these 2 points. You measure this is the final length, right? Initially this length is low because this is the deformed shape, deformed length, right? So in that case, if you consider initially these 2 points to measure the change in the length, so finally it is still the distance between those gauge marks, right? That is the LF distance, right? So L naught is the, as usual, the original length, right? That means before break, right? The before break, maybe it is like this, no, before breaking, right? So your gauge marks are still here. So this length is the original length, L naught. After breaking, this is LF, like that. Okay. Then other way is the percentage reduction of area. You know, when we identify that, yeah, it's that we call in Sinhala Thanya materials, that is correct, right? So in measuring ductility, we can use the reduction in area. When we applied stress is exceed the tensile stress, I told you that material starts necking, right? Then at that point, the cross section becomes smaller and smaller, and ultimately it will break, right? So Piyumar, do you have a question? You have raised your hand. NUD Piyumar, do you have a question? If not, okay. Okay. Then when that happens, right, the percentage reduction in area means percent change in the cross-sectional area at the point of fracture before and after the test. Fracture means the break. After break, you can roughly measure the cross-sectional area of the specimen, right? That is the AF. AF is the final cross-sectional area of the specimen at the fracture surface. That means it break at a particular point. At that point, what is the area, right? This is the percentage reduction in area. So we can use these two measures to have a kind of idea about the ductility of a material, right? So here is example. I will give you the answer because it's not a difficult one. You can read the question. The aluminium alloy, it's okay, has a final length after failure. That means after breaking, the final length is 2.195 inches and the final diameter is this amount after breaking, right? So calculate the ductility of this alloy. Then we have to show the values for elongation and percentage reduction in area, right? Percentage elongation, the expression is LF minus L naught over L naught, right? LF is the length after failure, that is 2.195. Initial length is 2. So you can calculate the percentage elongation, right? The percentage reduction in area at the fracture surface, the final diameter is given, right? That is 0.398. The diameter, but here it is a cross section, but it doesn't matter. But here you have to put the square terms. Why? Area is 5d squared over 4, right? So here diameter is the original diameter 0.505. Then 5d squared over 4 for the original cross section, 5d squared over 4 for the final cross section. Then the diameter is 0.398. Right? So over this here it is 5d squared. All 5 and 4 terms cancel, so that's why it is the square root of the diameters, right? So you will receive the answer as 37.9%. Okay, so this is how we calculate the ductility of the material based on the information we get from a tensile test. right? So then we move to the hardness, right? So we talk about the modulus of elasticity, then the ductility, then the hardness. It is also a mechanical property of a material, right? So hardness, it measures the resistance to penetrate of the surface of a material by a hard object, right? It means this kind of a, we say that it's a tadabak, right? So in that case, we try to use a hard object to make a penetration on a certain surface, and we measure the resistance given by the material. That's what we call the hardness, right? So it represents the resistance to scratching or indentation and a qualitative measure of the strength of the material, right? So this hardness, we usually do hardness testing, right? But that is a qualitative measure, not a direct indication of a strength of material, right? Usually we use two tests. One we call Brinell test, other one is Rockwell test. This is the test to measure the hardness of a material, right? We have a Rockwell test machine in the university to measure the hardness, right? It's a Rockwell test machine. So actually it depends on how you calculate it and what kind of material you use to measure the resistance, right? So in the Brinell hardness test, a hard steel sphere, usually 10 millimeter diameter 10 millimeter, is forced into the surface of the material. That means we put this 10 millimeter diameter hard steel sphere and we press it into the surface of the material, right? The diameter of the impression, that means it will make this kind, we call it the impression, right? This kind of a change in surface, right? The diameter of the impression typically it's 2 to 6 millimeter we measure, right? Then we calculate the Brinell hardness number with this equation, right? Then F is the applied load, because you have to apply certain load to make that impression. That means the change. That means change in the surface, right? So F is the applied load. D is the diameter of indenter. The material we use to make that impression we call indenter, right? That means this, in case this is a small ball, right? So D is the diameter of the indenter in millimeter, right? So diameter of the impression, that means it will be a circular shape, the impression, right? It will have a diameter, right? So diameter of the impression in millimeter. You have to put those values in here to calculate the Brinell hardness number, right? So actually in the Rockwell test, the indenter we use, it can be different, right? Based on the material you test, right? I told you in Brinell test, we use 10 millimeter ball as the indenter, right? But in Rockwell test, you see it can be a ball or a braille like this, right? Depending on the material you test. And also the applied load, it depends on the material and as well as this indent. For example, in this Rockwell A, right, it can be used for very hard materials, right? So you can apply a load of 60 kilonewton and you can use a braille, this type of braille. Or else high strength steel, this type of load you may need to apply again with the braille or like that, right? You have to choose the rail or the ball, the indenter type, based on the material you test, right? Usually in that Rockwell hardness test, you can automatically get a value for the hardness from the scale it has, right? You don't have to do that kind of calculation, right? You can search for this Rockwell hardness test. There are a lot of videos available in the YouTube also to demonstrate the Rockwell hardness test, right? So here is example. I think it's no need to explain because just to substitute of the values, right? So this is the binary hardness number calculation. It used a 10 millimeter diameter indenter and a 500 kilogram load. Indentation is 4.5, right? So just you have to put the values, substitute the values, and you can calculate the hardness number, right? So I wanted to explain a bit about the temperature effects on the mechanical properties of materials, but I will continue with that in the next lecture because I think now you have learned enough for today, right? So we will learn this effect of temperature on the mechanical properties of the materials from next week onward, right? So I will upload the slides up to here now and the recording in the evening, right? So if you have any question, actually I can do that. One thing actually I was thinking, one said, Savindu Hasanka, he said that, can you upload the PDF day before the lecture? Actually, I was also thinking, but you know, sometimes I solve the examples in the lecture, right? In that case, if I upload earlier, you won't have that answers with you. If you can note down those answers while doing the lecture, it's okay for me to upload earlier, right? So then, okay, I will from next week onward, I will upload the PDF earlier, and then there may be some examples without answers that I will do it in the lecture, right? So those answers, if they don't have in the PDF, please note down because I cannot upload it 2 times, right? In that case, we will do like that. Okay, no problem. So can you please give us 2 weeks for the assignment because our English knowledge is weak. Actually, for these things, you don't need English because I will probably not ask you to write that essay type questions, right? Your English is important if you are writing essay type questions, right? Mostly here I will ask you to draw some graph and do some calculations like that, right? So the reason I don't like to give you extended time periods for the assignments is you will have a lot of assignments accumulated with time with other courses. Isn't it easy for you to finish one by one as soon as possible, right? So if I give you 2 weeks, you will have another 3 or 4 assignments from other courses. So you will have a lot to work at the end, right? So I will not test your English, so you can use simple English and probably you won't need to write more long sentences in English in this my part, right? So someone asked to Nimesh explain some difficult English words from Sinhala. I am okay with that, but the problem is there are not only the Sinhala students, right? We have here the Tamil and Muslim students also, right? I will time to time I will do it, but I prefer to do it in English, thinking of all the students, right? So if you have any, if you think I'm speaking quite fast, you can tell me. I can slow down and explain bit by bit, because I know sometimes I am speaking fast, right? Because everyone, even when I go to university in the first year, we don't know much about, we can't speak English, right? We can barely write a sentence. But for engineering side students, I think you will improve with time. No need to afraid about English. Never think about that you are afraid, you cannot write, you cannot speak like that. You will improve with time. Okay, don't worry about English, right? Okay, I will slow down the speed. Someone said to slow down. Then I will stop for today, and we will meet next week, right? I will upload the PDF now. Okay. So thank you for your active participation, and I am happy that we have more than 100 students for the this lecture, right? So please follow, and please, if there are any difficult parts, please read again, and please refer the reference book also. Right? So I will stop share, and I will stop the meeting, and thank you for the participation. One more question. Okay.